Hello everyone. So in today's session, we are going to derive these two basic derivation of your three-phase induction motor, which is the part of the electrical machinery. Okay, AC machine basically. So before deriving the starting torque of three-phase induction motor, I want to discuss a very short concept of regarding this two derivation. Okay. So we know the induction motor has two part, which is stator, which is the stationary, and one is the rotor, which is the rotating part of it. Okay, so the stator has in equivalent circuit of induction motor, the stator has some parameters like R2, X, R1, X1, okay, E1, which is induced EMF, okay, Z1, etc. Okay. And in the rotor, we have R2, X2, E2, Z2, power factor you can say cos phi 2. Okay, this all. So we have to know that the torque, rotor torque, we are going to find the starting torque of rotor because stator is stationary. It is stationary part. It is not rotating, so it has no starting torque. Okay, stationary. Okay, so rotor torque. So the torque developed by rotor, the torque developed by the rotor is proportional to three most important terms. Okay, first one is rotor current, which is generated by I2. Okay, second one is your rotor EMF, which is E2, and the third one is your nothing but power factor. Okay, uh, I can write I1 and there is I2. These are the parameters. So these are the three termin what I can say parameters. The rotor torque, the torque developed by the rotor is fully proportional. So we can write by seeing these three equation uh, parameters. So I can write torque is proportional to your E2 I2 cos phi 2. Cos it is proportional, so I can multiply three terms. Okay. So I can write mathematically K is the constant and the same as it is K2 I2 cos phi 2. All right. So this is a very vital equation of torque, rotor torque. Okay, you can write this TR, rotor torque. Okay, so now to finding the starting torque, I can write that rotor impedance, rotor impedance, impedance, and I'm going to consider all the what I can say is per phase. Okay, because the equivalent circuit parameters which we write here is all about per phase equivalent circuit. Okay, so rotor impedance per phase, which is denoted by Z2, as I said earlier, Z2, this is Z1. Okay, so this is for rotor. So Z2 is equal to what? Uh, a minute. R2 square plus X2 square means the rotor resistance square of rotor resistance plus the square of rotor reactance. All right. So this is the equation. Now I'm going to find I2. or you can say rotor current per phase. So the current is E2 by Z2. As we all of know, in circuit theory, we studied this all type of what I can say formula that induced EMF is current into impedance, or you can say impedance Z is equal to induced EMF by current, or this is another relation. So many relation is we can write down. Okay, so E2 as it is, cause E2 has no such value, and the Z2 we find here is R2 square plus X2 square. All right, this, and now I can write the power factor which is cos phi 2. So power factor of the rotor side is the total resistance by the impedance. This is the formula. Okay, so R2 as it is R2, sorry, and the Z2 is R2 square and plus what, X2 square, X2 square. All right, now I can write starting torque, what, the formula I get here, which is this K E2 I2 cos phi 2. This is the rotor torque. Okay, so I simply write the formula here. So now again I am boxing this formula because this is very vital formula. So now simply I have to just plotting the formulas. So K as it is, E2 as it is. Now I2. This is the formula value of I2, which is E2 by root under R2 square plus X2 square. All right, and which is multiplied by cos phi 2, which is this formula, this value. So I can write it multiply by R2 by R2 square X2 square. This is very simple. Now is equal to what I can write, K E2 into E2 square. Okay, R2 as it is, whole divided by same terms, and it is having square, so I can write it R2 square plus X2 square. If you have any difficulty while I am going through this derivation, you can write in the comment section, I will answer that. So this is the value we get. Okay, so generally the stator supply voltage which is constant, so the flux per pole phi, we know the flux per pole is set up by the stator when it is fixed. So the turn means the EMF induced it, which is in the rotor, will be constant. Okay, so we can write finally Ts is equal to K1. I can write the another constant here, R2 whole divided by what, R2 square plus X2 square. Okay, so again I can write that K1 R2 as it is, and this is what, impedance, means Z2 square, the square of the impedance, same. This is the another constant I say here, and so it is clear that the magnitude of starting torque would depend upon the relative value of R2 and X2, that is rotor resistance and what, per phase, and standstill rotor per phase. So it can be shown that the K, this K, I can write that K is equal to 3 by uh, 2 pi ns. Here ns is the synchronous speed. Okay, so if I put this value in the starting torque equation, so we can write 3 by 2 pi ns multiply by a2 square r2 by r2 square plus x2 square. All right, so this is our, and another one is ns here is in rps. Okay, revolution per second method. Okay, so this is our required starting torque equation in rps. Or if you can, you want to draw, you want to write the same equation in rpm, then divided by 60 and you can get the same value. Okay, so this is our, so this is the basic equation. What you have to remember is this, and this is the, you can write yourself also. Now let's do the condition of maximum starting torque. Okay, so now it is too easy to find that because we derive already the starting torque. So the condition of maximum starting ts, I can write ts. Okay, so here I can write ts already. Okay, so it can be proved that the starting torque will be maximum when the rotor resistance per phase is equal to stator standstill rotor reactance per phase. Okay, so now I can write the ts is equal to, I'm going to write this equation, this, okay, which is k1 into r2 by what, r2 square plus x2 square. Okay, so now I am going to differentiate with respect to r2. Okay, so I can write that dts by dr2. This is simple derivation of this, and the k1 is the constant is out, and in the bracket I can write the derivative of r2 square remains the first one, that r2 square plus x2 square, and that is r2, and 1 is the power, that is 2r2, that is equal to this square, 2 plus x2 whole square square. Hope it's right. Okay, is equal to 0. This is our maximum equation. So now I can write from here that r2 square plus x2 square is equal to 2r2 square. So I can write from here r2 is equal to x2. So this is our